Now, simple harmonic motion. Harmonic, what does it mean by harmonic in the context of physics? It's talking about oscillation, okay? Oscillatory motion. Now, when you think about oscillation, what's the first thing? How do you define what is really oscillation? Motion, a state of motion, right? Describe the state of motion, back and forth, right? Something that moves back and forth repeatedly. Or you can say something move up and down, repeatedly. What are the examples of oscillations? Example like the classic one, vibrating pendulum, okay, oscillating pendulum, right? We have pendulum, and what else? We have a metronome, right? A metronome vibrating, tick back and forth. Or it could be like a mass spring system, okay, a vibrating mass spring system. Anything else? I can also say tides, right? Water tides, yes, tides, right? Like, or piston in a car engine also vibrate back and forth, up and down. So these are the examples of harmonic, okay, oscillations, simple harmonic motions. Now, why do we call them simple harmonic motion? Is there a complex harmonic motion? Yes, there's a complex harmonic motion. So example of complex harmonic motion is like, let's say like a example of a bouncing ball. Okay, like a bouncing ball. So if I drop the ball at a certain height, bounces, and for each bounces, the height decreases. Okay, because energy loss. And if you sketch the graph, height against time, it slowly decreases and just taper off. Okay, just eventually will stop. Right? So this is we call damping. The process is called damping, losing energy. Okay, so in this example, we can also say that the ball is oscillating. Yes, it's going back and forth, but because there's this external force involved, like frictions, it's going to alter these oscillations. So as a result, we get not a simple harmonic motion, it's a complex harmonic motion, because this one you have to take into consideration all the frictional forces, and for every 2 pi, like for every 360 degree, it may not do the same thing, right? So the period may change, the amplitude changes, right? And the frequency may also change. So this is an example of a complex harmonic motion. But in this chapter, we're only going to focus on simple harmonic motion, okay? Which means that we don't look at all the other factors that could affect it. Okay, so again, there will be an assumption made, right? So let's take an example of a simple harmonic motion. Like, okay, the best way you think about it is like this. Suppose that there's a person like doing a swing, okay? So we let me draw it here. At the original position, he started here, right? This is, we say, the equilibrium position. Okay, the equilibrium positions. Now, when he's displaced to one side and let go, he'll swing back and forth, right? Left and right, back and forth, and it's actually symmetrical. Okay, we are going to assume that it's symmetrical. Okay, now looking at this motion, simple harmonic, yes, but how do we define simple harmonic motion? What is the element needed to be there for us to say, okay, this is simple harmonic motion? Now, the first thing is the force. When the person is being displaced, there's a force created. Okay, there's a force created from where? From the tension and the mg, right? When it is displaced, the tension and mg changes orientation, so it creates a force. Later we'll look at a mathematical standpoint, but here we just look at the concept. Okay, so the moment he is displaced, a force is produced. So whenever there's net force, there will be an acceleration, and this force causes the person to return to his original positions. Okay, so each time he swings away from the equilibrium position, he will always return back. Swings to the right, return. Swings to the left, return. Who is causing it to return? it is the force, right? The force created. And notice that the force is always pulling it back to the fixed point, back to the equilibrium position. So in other words, the force is always directing towards the fixed point, regardless of your position. You are here, the force is always pointing towards the fixed point. I can also say that whenever it swings to one direction, there's a force in the opposite direction. It swings to the right, force acting to the left. Swings to the left, force acting to the right. So that is the first element. That is the first criteria for a simple harmonic motion. That is, we say the force is acting in the opposite direction. Okay, or we can say, usually in the notes or in the textbook, it says acceleration instead of force. So acceleration acts in opposite direction. Always. Okay, to what? To displacement. Right? Now, number two, the second thing is, if this person is being lifted higher up, what happened to the return? Is it going to be fast return or slow return? Let's say it's doing like this, he's raised at this point here, compared to this point higher up. This one is going to experience a greater return, like a faster return, right? In other words, it's a greater force, a greater acceleration. Okay, so that means the further away you move from the equilibrium position, the faster, the higher the force acting on you, and the faster the return. So the acceleration is higher. Same for both sides. Okay, so we can also say that the acceleration experienced by the person, okay, the acceleration is directly proportional. Directly proportional to what? To displacement. These two must be fulfilled, because if only one is fulfilled, one is not fulfilled, let's say the first one acts in opposite direction, that is not fulfilled. What happened? Acceleration is directly proportional to displacement. That means that the further you go to the right, the more the acceleration in that direction. So it will swing away, something like that. Okay, you can imagine that, right? So the first one must be true as well. Acceleration must be in the opposite direction. So it always come back. Okay, huh? Now, the force comes from the tension and the mg. In other cases, in other examples like the mass spring system vibrating, where does the force come from? The moment you displace the mass, the force created is from the intermolecular forces of the spring, right? So the spring, what is the nature of the spring? Whenever you disturb it, it wants to come back to original condition, right? So whenever you displace it, there's a force produced that we call the restoring force. In the case of the metronome is a bit different, because there's a force coming from the internal to keep it tick back and forth at the same rate, right? At the same period. Okay, it cannot have damping. So there's an external force internal to cause it to tick at the same period. All right, car piston. So all this, in every situation, the point is, in every situation, there's a force involved to bring it back to the original position, the equilibrium position. Okay, now, so now you know how to define a simple harmonic motion. Okay, let's look at, from the mathematical aspect, how do we define simple harmonic motion, the equations, the derivations. So first thing is that we want to understand is that we will apply what we learned in the force. Let's say that this is, we take one pendulum and it swings to one side. Okay, this is the angle, and let's take, this is the length of the string, and this is the distance. The distance is actually curve. The displacement, I'll put it as x. Okay, let's derive some equations here. What we know about geometry is that S equals to r theta. So we change this to x. the radius is the length of the string, L theta. And then we do theta equals to X over L. Let's put it aside first. Then we analyze the forces. Okay, the forces. We have mg, and then we have tension. Here, if I resolve it in this direction, this would be mg cos theta. Right, so you have this line, vertical line, is parallel with this one, so that means the angle here is the same as that one, mg cos theta. And if I resolve it in this direction, this one is mg sine theta. Okay, so we know that mg cos theta, oops, let me change a bit. We know that mg cos theta balanced by the tension. And then we have another one is the mg sine theta equals to, is it balanced by any forces, any other forces? No forces, right? Only that one. That means that it is the net force. So this one become MA. Okay, now this one, net force equals to MA. So cross out the M, I have G sine theta equals to acceleration. Okay, what we do here, from here, we use this small angle approximation. That means we say that sine theta approaches theta if theta is a very small angle. Sine theta is actually equals to theta if it's a very small angle. Now this is in radian. Radian, if it's degree, you can convert to radian. They found that it's actually around 0.244 radian. When you put it in, you sine 0.244 in radian, then you get almost the same, 0.244. Okay, so this is like approximation. Approximation, okay? They call it the small angle approximation. So 0.244 angle, if you calculate, put in the calculator, you sine this one, you get the same. Or any angle below it, smaller than it, 0.1 or 0.0 something, okay? You get this one, it is almost always equal to theta, sine theta equals to theta. But anything higher than this one, higher than 0.244, it will start to deviate. This thing will start to break down. Okay, no longer equals to this one. Now, what is 0.244 if you convert to degree, right? It's about 13.99, okay, let's say 14 degree angle. Okay, so we are going to use an assumption that the simple harmonic motion is between very small angle, about 10 degree angle. Okay, 10 degree angle. Later I'll explain why. Okay, so here, from here, then this one I become G theta. Okay, sine theta become theta for a very small angle equals to acceleration. Okay, then we put in, putting equation 1 into equation 2. Right. So G X over L equals to A. And then I take the X out, exchange places with the G. So we have G over L equals to A. Now from here, I have to cheat a bit. Okay, because you see, the acceleration is always opposite to the displacement, correct? Displacement is my X, acceleration is my A. So that means that we have to add a negative. So when X is negative, acceleration is positive. If X is positive, acceleration is negative. So we add a negative here. We cheat a bit. Okay, because this is, I'm doing the mathematics, but I combine with the physics. Right, so I put the negative here. I get A equals to negative G over L X. And this is actually a constant. The G is a constant. The L is also a constant. So that means I can write A is directly proportional with minus X. This expression fulfills these two conditions, which is first, when the displacement increase, acceleration increase. Second is that they are opposite direction. Okay, so this is the definition of defining SHM, simple harmonic motion. Okay, the constant, right, G over L, the scientists, they decided to choose a quantity, the omega. Instead of writing this one, they decided to put A equals to minus omega square X. Okay, this is us again, this is like the G over L is the constant value. Why they want to put squares? Because they want to just because they want to make it positive, right? So you get this equation A equals to minus omega square X. This is for the simple harmonic motion, right? So force equals to MA. We put it in, that means we get minus omega square mx. That is my resultant force here. Okay. Right, so we're done with the derivation of the A omega square X. Now we look at the next part. The next part, let me erase this, get some space here. Okay, now I want you to draw a table, just a simple table, showing the comparison between each quantity. Like we are going to look at the important things of a simple harmonic motion. We're going to look at the speed. Definitely, always you'll be asked the acceleration, the displacement, and also the period and frequency. Okay, so you do a table, and then you write position over here. Write position, and then we do one column for the displacement, one column for the speed, one column for the acceleration, and one column for the force, just to see how this changes when the object vibrates, okay? When an object oscillates. Position, we're going to take three positions. First is the middle, of course, the equilibrium position, A, and then left, right. Okay, so left, we put left, center, and right. Now, I want you to put in, just to kind of spend like 1 or 2 minutes to fill in the answer for each quantity. I want you to fill in, either you say, okay, it's maximum or 0. Okay, it's either maximum or nothing, 0. And then you also fill in the sign. The sign is either left or right. That means positive, okay, sorry, negative or positive. Okay, now example. For the displacement, when the position is at the left side, what happened to the displacement? The displacement has a sign, right? So anything to the left is a negative, anything to the right is a positive. So the displacement is a negative, and at the left, this point is the maximum displacement. So I'm going to write here max, and then minus. Okay, now I'll give you 1 minute. You try to fill in this one, and I will write down the answers after that. Okay, let's look at the answers. Position at center, displacement is 0. Position at right, displacement is again maximum, but is a positive. Velocity, left, velocity at the outermost point, that is the turning point, right? The turning point, so V is 0. And at the center, it is the maximum. V is maximum. And what is the sign? Now, the sign here, it can take positive or it can be negative, because it can be swinging to the right or it can be swinging to the left once it reaches the center, right? So it can be positive or negative. Position at right, so velocity is again 0. Now, acceleration, left, okay, acceleration is related to the displacement. If displacement is maximum, acceleration also maximum. Maximum, but it's opposite to displacement, right? So this one would be positive. So when he swings to the left, the acceleration would be acting to the right here. And center, acceleration would be 0, because it's already come back to the equilibrium position. And right, again, it is a maximum, it's a negative. Force is the same as acceleration. So maximum plus 0, maximum. Okay, because F equals to ma, they should have the same direction. Okay, they are directly proportional. Right, so it shows that all the changes of displacement, velocity, acceleration, and force in a simple harmonic motion. Now, next one, we will look at the graph part, the graphical representation of the 4 quantities here. Now, again, let me, if you want to take down this one, you can screenshot, because I want to erase this on the right side. Okay. So far we know that acceleration equals to minus omega square x. X is displacement, and the displacement changes over time, right? So how the displacement changes over time for an oscillating object? Take starting from the right, okay? You can start at any extreme. Let's say we start dropping the object, we start vibrating, oscillating the object at the extreme. So it's either left side or right side. So that means from here, we separate into 4 sections, right? Because we know that if you start at the right side, you swing to the left and then you swing back to the right, that's one complete oscillation, correct? So if you break it down into 4 sections, the first one is from the right to the center, and then from the center to the left, that's the second one, and then come back from the left to the center, and eventually the last one is center back to right. And each section is 90 degree, 90 degree, 90 degree, 90 degree, and 90 degree. So it adds up to one whole revolution, 360. Okay, so to plot the displacement against time, so we have here, we have positive, negative, and we do another time axis. First, we start at the amplitude, okay, the extreme here. This distance here is the distance from the equilibrium positions. So I'm going to draw this. How does the graph look? the graph looks like this. First, it's going to curve downward to this point because starting at positive, at the right side, it's positive displacement, right? So it would be above the x-axis, and then it curves down. Okay, why it curves down? Because the velocity is increasing, right? The velocity increasing. So your motion graph, the displacement time graph is like a curve down. And then to the center, so this section, this quadrant is moved to the center. And from the center to the left, now you're moving in the negative direction. Displacement increases in the negative direction. So here I continue to draw increase in the negative direction until maximum. Maximum, and then again, the third section is returning back to center from the left, right? From the left, return to center, and then the whole thing repeats, right? The whole thing repeats. So as a result, you get something like this, a cos graph. Okay, if I extend it further like this, a cosine graph. Now a cosine graph, you get cosine is because I start timing when it is at the right, when it is raised at that position, right? If I start timing at the center, then your graph would be different. Okay, it will start from the origin over here. Okay, we start from this point over here. But if I start timing from the extreme, from the amplitude, okay, when it is lifted, then you get a cos graph. Okay, now the maximum displacement measured from the equilibrium position is, we call the amplitude, right? Let's give it a symbol. Let's put it R here. Okay, R amplitude, and this is also amplitude, negative R. This graph shows the displacement against time graph. Okay, later I give you time to draw it. Now, this X is the displacement time graph. Okay, try to sketch another graph, which is the acceleration time graph in the same graph. Okay, let's look at acceleration. Now, what do you know about acceleration? Acceleration is maximum at where? At where? Okay, look at this table here. Maximum when the displacement is maximum, right? So you look at the displacement time graph, the curve, where is the maximum? Over here. That means acceleration is also maximum, but opposite direction, right? So if this is positive, then acceleration will be down here, negative here. Okay. Now, I'm not drawing this according to scale. So please don't think that, okay, acceleration has the same magnitude as the displacement. No, right? So I'm just, this is not according to scale. So we just want to know the shape of it, right? So we start here to here, and the maximum displacement over here, maximum acceleration would be opposite over here. So we join like this. Again, where is maximum displacement? Over here. Okay, so we flip it, maximum acceleration over here. Like this, and then we join like this. Oops. And then like this. All right. So the inverse cosine graph. And this graph is the graph of acceleration against time. What is this? How about velocity? Velocity, okay, we sketch velocity curve. Now velocity, look at the maximum. Where is the maximum velocity? Maximum velocity is at the center, right? Center, that means when the displacement is 0. Okay, when the displacement is 0. Now I want you to look at this part from here to here. Let me highlight it. From here to here. The object is moving from, starting from the right, swing to the center, right? This part of the graph, the yellow shaded region. The object is starting at the right, swinging to the center. Focus on the velocity. When it starts at the right and swing to the center, what is happening to the velocity? Increasing, right? Increasing. So at the center is the maximum. And what about the direction of the velocity? Is it towards the left or is it towards the right? Towards the left. Because you start swinging from the right, you're moving to the left. So as it reaches center, the velocity is a plus or a minus. The velocity is a minus because it's facing to the left, right? So you can already guess the point at here. Where would be the velocity point? The velocity is a maximum and it is a negative. So down here. At this time period, this is the velocity. Okay, this is the curve of the velocity. So I start drawing from here, 0. Velocity should be curving like this. Now again, see here, maximum velocity. Where is the next maximum velocity? It swings to the left, swing back. Again, you get the maximum velocity, but this time it is facing to the right. That is a positive. Okay, that's a positive. So where is it? Where is it? When, over here, right? This point. When the displacement is 0, which means when the white line crosses the x-axis. So at here, the velocity is a maximum and it is a positive value. So it's up here. Okay. Now, the same thing, you can already guess the graph here. Maximum displacement, velocity is 0. Maximum displacement, velocity is 0. And I can draw the curve. This. Something like that. Okay, a bit cha-cha. Let me position it a bit. Okay, like that. So this curve is velocity against time. Understand how to draw the curve for velocity, acceleration, and displacement. Okay, and notice that now once we have everything in one graph, notice that this one, the displacement is 90 degrees out of phase with the velocity. 90 degrees out of phase. And the velocity is again 90 degrees out of phase with the acceleration. What does it mean by out of phase? It's like lagging. Okay, let me give you a perspective here. You see, let's say I have a pendulum. Again, we take the right, center, and left. The first pendulum number 1, I swing it. I let go at this position on the right. Okay, so it swings to the center. This is 90 degrees, right? One section of the revolution. Okay, one quadrant of the revolution. So 90 degrees here. When the pendulum reaches the center, I swing another pendulum starting from the same starting point on the right, like this. Okay, the moment that this orange pendulum reaches the center, I let go of the blue one. So again, it starts swinging. So if you compare these two vibrations, these two oscillations, the blue one, I can say that it's lagging because the orange started first. The blue one start later, right? How late? After 90 degrees. After the first one has gone 90 degrees of the journey, the blue one start. So you can kind of imagine, right? You can kind of imagine if I let these two things vibrate, then we say that these two pendulum, they are out of phase by 90 degrees. Okay? They are out of phase by 90 degrees. If they are out of phase by 180 degrees, how does it look? That means that the first pendulum reaches the other end, 90, 180. Then only I let go the blue one. Okay? So they will be swinging completely opposite to one another. This one to the right, this one to the left, like this. This is 180 degrees out of phase. Okay? So this one, they are 90 degrees out of phase with each one another. Okay, so how do we get this graph just now? We get it by looking at the position, right? The velocity and stuff. Actually, if you want the mathematics, okay, from mathematics, how do we get the velocity graph? The velocity, actually, we can get it by the differentiation, okay, differentiation of the displacement time graph. So we have the displacement time graph. Okay, first off, what is the displacement time graph? How do we have an equation defining this displacement time graph, the white color one. We write it as x equals, so it's a cos graph, right? It's a cosine graph. So I will write r cos omega t. Okay. What is this formula? You can see. What is omega again? At the first glance, okay, what is this? At first glance, we don't know what is this, right? All this makes confusing. So actually, it's the same thing. You see, omega. What is omega? Omega is angle over time, right? So if you take omega times time, what you get? Omega times time is just angle, right? So it's the same thing. This is just angle, cos angle, right? Cos angle. So it's like a cosine graph. Cosine graph, and then beside it is the r. That is the amplitude. That's the amplitude, the maximum amplitude. Okay. So the way you think about it is like this: x is displacement at any time, at any point in time. Right? It can be here. It can be here. It can be here. At any point in time, the displacement is a fraction of the amplitude. This is a fraction. Okay, you just times the r times by the cos omega t, a fraction. So at any point in time, the displacement of the object is a fraction of my amplitude here. Okay, so this equation represents this curve here, this curve here. Yeah, so this equation is the, you have to remember this one. You are going to need this in the calculation part. And then the velocity, we can get it by differentiating this equation. Okay, if you don't like how I explained just now, okay, I want the mathematical proof. Okay, sure. Then you derive this, you differentiate this one. Okay, dx over dt, you get something like, okay, v equals to, if you differentiate this one, right, you get v equals to cos become minus sine. Okay, differentiate cos become minus sine, so you get something like minus r omega, and then sine omega t. You get this. Okay, so this is the equation for velocity. How do I get this again? We take the first derivative, the differentiation of this one. You get this one. So this one is actually the sine graph, the blue one. You can see it looks like a sine, right? But it's inverse because you have a negative in front. Okay, guys, I give you a few minutes. Okay, you draw this in a piece of paper in your exercise book. This graph, and also make sure you have the table in a few minutes, and we go to the next one. First derivative is what? Differentiate is means finding gradient, right? So in other words, you can think of velocity as the gradient of the displacement time graph. Okay, if you look at the white line, what's the gradient here? This point, let's call it point A. What's the gradient here? At the turning point. At the turning point, the gradient is 0, right? So that's you see the corresponding V is 0 here. Again, this is another turning point, B. What's the gradient here? The gradient is 0, so the velocity is 0. All right, let's continue. Let me open up my document first. Okay, now you should be seeing my PDF that shows all the formulas, not all, the common formulas that you're going to need in the calculations part. All right, now we look at one by one. See, yeah. So we have 4 columns: accelerations, and we have the speed one, the displacement, the period, and frequency. Okay, so the first one, you're already familiar with this one. A equals to minus omega square x. And then the second one, this one, how do we get this? This one we get by, okay, from here, x, a equals to minus omega square x. We know that x is equals to r cos omega t, right? So we just put it inside. We get a equals to minus r omega square cos. Okay, this one actually there's a mistake here. You should add r inside. Okay, r omega square. R omega square cos omega t. Okay, so the way we derive this one. And then for the maximum acceleration, now maximum acceleration is when this one is when the amplitude, when the displacement become the amplitude. Okay, when it is at the extreme, the left or right. So when x equals to r, that is where the acceleration is maximum. So if you put it into the equation, you put it inside this, a equals to minus square r. So a maximum equals to minus square. This one is x. This one is x, and then this one's r. Okay, so since we are only looking for the magnitude, so we get rid of the sign. Only the magnitude. The magnitude is a max omega square r. Okay, so that's how we get these 2 equations. Now looking at the second one, the speed equations. The speed equation, first one is this one. This one, we don't need to know the derivation of it. It won't be asked. Okay, it won't be asked. This one, written in a different way, is like this one. Maybe you're more familiar with this. V equals to plus minus omega, and then you have a square root r square minus x square. It's the same thing. I'm just moving the square over there. Okay, so I write this here because maybe your teacher teach you this one. You're more familiar with this one, but it's the same thing. Okay, but we don't need to know how to derive this one. And then this one probably you already know. This is from the differentiating the x, right? So we have x equals to r cos omega t. If we take the dy dx, we get this. dxd dt equals to v equals to minus r omega sine omega t. What about the Vmax? The maximum velocity occurs when the displacement is 0 at the center. Okay, so when x equals to 0. If x equals to 0, you put in the equation, the v square equals to omega square r square minus 0. That means you get V square equals to omega square R squared. That's V equals to omega R. Okay, that's how you get this. V max. I'll write it. V max equals to. Oh, I cannot erase that one. For some reason, I cannot erase this. Never mind. V max equals to omega R. Okay, now this one is the displacement time, this one, equation, okay? And maximum amplitude, maximum displacement is equals to R, maximum amplitude. And this one is from the circular motion, okay? How do you get T equals to 2 pi over omega? Omega equals to is angular velocity, right? This is angular velocity, that means angle divided by time. If I fix it for one oscillation, that means the angle is 360 degree, 2 pi, over the time is become the period T, time for one oscillation. Okay, so T equals to 2 pi over omega. That's the first one. Okay, and omega equals to, I can also have, I write it here, up here, omega equals to 2 pi over T, and T, since T equals to 1 over F, so omega equals to 2 pi F. So these are how all these equations are derived, okay, are derived to become what you see here in the table. So this table here is already tabulated all the formulas that you're going to need in the calculation of the simple harmonic motion. We are not going into the energy yet. That one we'll leave it for the next lesson. Okay, today we only focus on the period and velocity acceleration calculation. Now it makes look a bit overwhelming at first because you see so many formulas, right? Which one to use? Now here's one tip I give you. You see, you focus on the angular velocity, the omega, because you see, all the formula here got omega, right? Omega, 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 omega. So all the formula got omega. Without omega, you cannot find. So focus on the omega. If you are given the period or the frequency, you find the omega first, right? Same thing. If you want to find the period and the frequency, you find the omega first also. Because without the omega, you cannot find the period frequency, right? So focus on omega. Of course, for the questions given to you, you want to know very clear what you want to find and what you are given. Okay, what you want to find and what you are given. Is that omega? Okay, if no omega, then you find omega first. And tip number 2 is if time is not mentioned, if no time, then most probably we are going to use this one. Because this one has no time in it. Okay, these equations, all the cos, the sine thing, this one, it has a T there, meaning that it shows what is the value of V at a certain time, what is the value of acceleration at this specific time. So if time is not given, then you're not going to use that. We are going to use only this one. Okay, the V square equals omega square R squared minus X squared. And number 3 is that if the question did not mention any maximum thing, then most probably you're not going to use that, the maximum formula, A max, V max, X max. If the question did not mention anything about the maximum, then you don't need to look at all this formula here. Okay, so use these 3, the calculation becomes very easy. Now, a few things I want to point out also is that later I'll show examples how to show this, how to do this one after our break. So one thing is that we have the formula X equal to R cos omega T, right? This is showing the graph of displacement against time. This is the cos graph. One thing you need to know is that this graph is showing that where do we start timing? Where do we start timing the oscillation? We start timing when it is at the maximum point, when it is lifted. Okay, on the right side or left side. So if the question says that, okay, we start timing when it's at this equilibrium position, then we use x equals to r sine omega t. Okay, so the difference is that this one starting from 0, like this. So this is, we start timing when it is at its equilibrium position. The same thing with the velocity. You see this velocity equation here, which this one. This one assumes that we start timing when object is at where? Object at max displacement. Okay, because this one we actually get it from what? We get it from this graph, right? We get it from the x equals to r cos. So it assumes that start timing at max displacement. Okay. And how about for the velocity? If we start timing from the equilibrium position, then it would be the opposite sign. That means that you have you differentiate this one, right? Okay, so let me write it down here. That means that you have like it's not given here. Okay, v equals to r omega cos omega t. This one, it assumes that timing at equilibrium position. Okay, v equals to r. Because when you differentiate this sign, you don't get a negative. So that's why you don't have a negative here. But if you differentiate this one, you get a negative. When you calculate the cos and the sine, remember that to change it, x equals to, wait, let me write it here. X equals to r cos omega t. This one, when you put the time and the omega in, you multiply, you get a number. That number is in radian. That number is in radian, so be careful. You either change it to degree before you cos it, or you change your calculator to radian so you can calculate. Okay, this one is in radian. You remember to change it. Okay, guys, I'm going to give you 5-minute break, and we'll come back after 5 minutes. And I'll show you the calculations examples, and after that, we'll do some exercise. Then we finish. Okay, so we come back at 8:08. 8:08. Okay, guys, we are back. Okay, we look at examples. Okay, example one, an object is oscillating with a simple harmonic motion. Its maximum displacement from equilibrium position is 0.2. The period of the motion is 0.1 second. Find its speed when it is 0.06 meter from its equilibrium position. Okay, what do we know? R 0.2, period of motion 0.1 second. Find the speed when it is 0.06 meter from equilibrium position. That means that is the x, 0.06 meter. Okay, now speed. Okay, referring to the table, how many formulas do we have? We have this one, we have this one, we have this one. Maximum speed is not mentioned, so we're not going to use this. Is the time given? Time is not given, right? No t. That means we are going to use the first one. V square equals to omega square r square minus x square. Okay, now first again, we want to find what? We want to find the omega. Omega. So from where? From the period t equals to 2 pi omega. 0.1 equals to 2 pi omega. 2 pi over 0.1. $62.8 radian per second, angular velocity, right? So radian per second. Now, then we put it in here. V square equals to 62.8 square, 0.2 square minus 0.06 square. Okay, and we take the square root. V is 12.0 meter per second. Example 2, a mass is moving with simple harmonic motion. Its displacement was at a maximum of 1.1 when t equals to 0. Okay, so that means r equals to 1.1 when t equals to 0, right? Its maximum speed is 0.33, so v max 0.33 meter per second. Find the frequency. Now again, we want to find frequency. What we want to have first, angular speed, angular velocity. So A, we find the angular velocity. So angular velocity given V max, we can find this angular velocity. V max equals to omega r, 0.33 equals to omega 1.1. Omega equals to 0.3 radian per second. So once you get this, only then you find the frequency. Omega equals to 2 pi f. F equals 0.3 divided by 2 pi equals to 0.0477 hertz. Okay. B, find its speed after 2 seconds. Is the time given? Yes, t 2 seconds. So we use the sine V equals to minus R omega sine omega t. V equals to minus 1.1, 0.3, sine 0.3 and 2. Okay, so this one 0.32, we put it as, okay, we have minus 0.33 sine 0.6. Again, this one is in radian, so you change to degree, 0.6 times 180 divided by pi. Then you can do like 0.6 times 180 divided by pi to change it to degree, and then you only sine it times 0.33. This one you get minus 0.186 meter per second. Okay, next one. Example 3 and example 4. Example 3, a heavy body is performing simple harmonic motion. Its displacement is at its maximum value, 0.40, when t equals to 0. It first reaches a point of 0.20 meter from its equilibrium point after 3 seconds. Okay, find the period of the motion. Period. So we want to find t. First, find what? Find W. Okay, find omega. So find omega, we have what? We have we can use this one, x equals to r cos omega t. Okay, because we have the t and then we have the x. It says that its displacement is at its maximum value of 0.40 when t equals to 0. And it first reaches a point 0.20x from its equilibrium point. This is the x after 3 seconds t. So we put 0.20 equals to 0.40 cos 1 and 3 seconds. Okay, then we find, okay, moving this one, we get, solve for this one, we get 0.349 radian per second. Period, 2 pi over 0.349. 18 seconds. You can also sketch the graph like this. If you have like, if I sketch the graph, right, you can see, okay, simple harmonic motion. Where is the, here is 0.40, the maximum amplitude. And it says it first reaches a point 0.20. That means half of this, right? Half of this, and it first reaches, that means is over here. 0.20. This is the first reach. And then here is second reach, right? And here is second reach, here is third reach, because the motion repeat. So there are certain, there are more than one instances where it is at 0.20 meter. But it first reached, that means it's referring to this point. Okay, so it says that after 3 seconds, that means here is 3 seconds. What is this? 3 seconds. 3 seconds, if you take like one complete oscillation from here to here, 1, 2, 3, 4, 5, 6, 7, 8. This is 1/8. 1/8 of the period. 3 seconds is 1/8 of the period. You can also do like that, okay? 3 seconds is 1/8 of the period. So period would be 3 times 8. Sorry, 1/6 should be, not 1/8. Let me change this one. Three times 6 would be 18 seconds. Okay, so question will always ask, why it says that it's the first reaches? Why is the first reaches? Because your answer is that because there can be other times when it come back at 0.20 meter as well. Okay. Now C, find the body displacement when its speed is 5 times 10 power of -2. Okay, we want to find the body displacement x when the speed v is this one. Which one do we use? Is the time mentioned? Is the time t mentioned? No, right? No t. So we don't need to use the sine cos. We use this one. V square equals to omega square r square minus x square. Okay, so 5 times 10 minus 2 equals to omega 0.349 square and then 0.40 minus x square. Okay, if you solve for this one, we get x equals to 0.373 meter. The rest I let you try. Okay, you try yourself. Example 4, you try. Okay, example 4. So body performs simple harmonic motion. Motion is time from point of maximum displacement. Motion is time from maximum. 2 seconds later, it reaches the equilibrium position. 2 seconds later, it reaches equilibrium, meaning that over here is 2 seconds. For the first time, its maximum acceleration is 0.60. Find its period. Okay, so period, this is 2 seconds. This is a quarter. 1, 2, 3, 4, 5. Four times this one. Okay, so period equals to 2 times 4. 2 seconds, 2 seconds, 2 seconds, 2 seconds. So 8 seconds is the answer for A. B is maximum speed. Okay, maximum speed Vmax. Vmax equals to omega r. Again, we need the omega. So omega equals to 2 pi over 8. 0.785 radian per second. And then Vmax is, okay, we want to find the A max, right? A max equals to omega square r. So 0.60 equals to 0.785 square r. Okay, given that this is the A max, not the V max, okay, A max. This one, let me erase this. Okay, then r equals to 0.974 meter. Then only you find the V max. Seven six four 0.764. Okay, last two questions. No. 4 and 5 and 6. Okay, for the first one, find the next 3 times when the displacement is at an extreme of the motion, right? So it will be easier if we can draw a graph. It says that a body perform a SHM with a period of 3 seconds. That means until here it's 3 seconds, starting at the extreme. The next 3 times when the displacement is at an extreme of the motion. So this is time 0. The first extreme is when? Over here, right? Over here. So it's half of 3 seconds, 1.5 seconds. Okay, 1.5, and then 3 seconds, and this one, 4.5. Maximum displacement. So 1.5, 3, and 4.5. B. Right, let's draw it on the same graph. Velocity is 0. How does the velocity graph looks? Over here, right? Here. So it's like, let me draw it like this. Okay. This one align with this one align with this one. Okay, it's 90 degrees out of phase. Over here, like this. When velocity is 0, so meaning that over here, and over here, which is the same, right? The same as the previous one. When velocity is 0, 1.5, 3, and 4.5. So your answer is also same, 1.5, 3 seconds, 4.5. Okay, when acceleration is 0, I'm just going to draw another one, too crowded. Few seconds. So acceleration is opposite, right? Opposite to displacement. So you just flip the whole thing. 0. Acceleration 0 over here, over here, over here. Okay, what is this? This is 1.5 second. That means this is 0.75. 0.75. The next one is this one. So this is kind of like 3/4 of the 3 seconds. That's 2.25. Okay, and this one is 5/4, 3 seconds, 3.75. Okay, calculate the following quantities. Amplitude, vibrate 20 cm, amplitude is half of it. So equilibrium position center, we take 20 divided by 2, 10 cm, change it, 0.10 meter. B, find the maximum acceleration. Again, maximum acceleration, we'll find the omega first. Omega first. So omega equals to 2 pi over period, 2 pi over 2 seconds. We get 3.142. Okay, then Amax square 0.10. That's for B. And the last one, maximum speed, Vmax 3.142, 0.10. Okay, we finished. Oops.